Hi, I'm Dr. Peter Leong, and I'll be taking you through this topic on large-scale machine learning, or what we call scalable machine learning. So first of all, we'll talk about the overview of this problem. Why do we need scalable machine learning or large-scale machine learning? Then we'll talk about some of the constraints that we would face. For example, a CPU constraint or a memory constraint as applied to machine learning. Then we'll talk about some of the techniques to handle this problem, such as gradient descent for large data sets. And then another method is to do what we call out-of-core learning, which is also called incremental learning. And these techniques are available in scikit-learn. And finally, we talked about how we can actually overcome some of the problems in training very large data sets in terms of not having sufficient computational power to actually be able to do it in a timely manner. So first of all, the overview of the problem. Right. Why do large data sets pose a problem when we attempt to build machine learning models with them? Actually, the problem has two parts to it. The first one is that the very large data set, we're talking about a billion rows of data or more. In other words, the data set may be 100 gigabytes in size. So the first problem is that such large data sets, we need actually to have a lot of RAM or memory in the computer to be able to store the data itself, right? So as we actually try to build the model, we need to be able to read in the data, and if the data set itself is very large, we will need to have a huge amount of memory just to be able to load that data into memory and be able to train the model using it. The second problem is that the output of the training process, the model itself, requires space to store the parameters as well. So if you have a very large data set to train from, then the model that you build may also correspondingly be pretty large as compared with a model that you build using a small data sets. A very large model like the more than a billion parameter model called GPT-3, it is definitely something which takes a couple of gigabytes of RAM just to store the model itself, not to mention the data set. So in terms of the memory requirement, having very large data sets of a billion rows or more, we do need to have more RAM to store the model as well as to store the training data. And of course, the in the training process itself, you need a lot of temporary space to also work on the working memory, right? To actually do the training process. The other problem that we will actually face is that we would also require a lot of CPU or computational resources in order to do the number crunching to actually do the training itself. So we need to really consider whether or not having more data is actually a good news for us. Okay, so first of all, we need to have all these additional resources for memory as well as for the CPU. But when we actually have more data, does it actually yield any improvement in the accuracy or the metrics for the model that we build? So this is something which we should really consider very carefully. Do we actually get any improvement when we use more data? Because the worst possible result that you would actually could get is that you acquire the resources, the couple of gigabytes of RAM to actually do the training. You acquire the necessary CPU resources to do the training, but in the end, actually, the model that you build does not actually show any significant improvement over a model that you built with less data and with less resources. So this is something which we are going to take a look at later. How do we actually measure the effectiveness of introducing more data? Because we don't want to have this result where we consume more resources, but we don't actually get any improvement from that consumption. So in other words, really is more or less, right? Doing trying to do more with more data, more CPU, and more training resources, giving you lesser result, or is it really less more? Trying to do the same training with less data, less resources, actually going to be more efficient and giving you a better result in the end. Okay, so what do we need? What if we need more RAM than what's present in your single computer? This is the other question. As I mentioned just now, if your data set is very large, then you will probably need a huge amount of RAM to do the training, both to store the training data as well as the model itself. If you need 100 gigabytes of RAM, this is actually far more RAM that you probably have on your laptop or on your single machine. A typical laptop only has about 8 gig or maybe 16 gig, or if you are you could afford it, maybe it has a 32 gig of RAM on your laptop, but not many laptops have a 64 gig of RAM. When you come to a server, a single machine may have a few hundred gigabytes. You may have 256 gigabytes of RAM, or even 512 gigabytes of RAM on a really large server. But what happens if you need 1 terabytes of RAM? Uh, those machines probably exist, but it is going to be a lot of cost involved to acquire that kind of machine. So are there other solutions that we can go for besides just looking for a really large server to do the training on? So this is the question that we should keep at the back of our mind, but we're going to take a look at the various possible solutions that we can use to solve this problem. And lastly, what happens if we need a really lot of computational power, 100 core CPU to complete the training process in a reasonable amount of time? By reasonable, I mean days rather than months to actually complete the training process. Now, your laptop may have 8 core or even 10 core. If it's a really powerful laptop on the server, you can have a couple of tens of cores, right? You can 64 core or 64 core. What happens if you really need 100 core or more to complete the job? Same as the previous problem. Yeah, we can go and try to get a very large server that has even 100 core of CPU resource, but they are very costly. Is there a better solution that we can use that to spread out the load over multiple machines, for example, instead of trying to find one single super machine that is able to accomplish all of this within one single server? Because if you are able to spread out the cost over multiple servers, then actually the scaling issue is a matter of acquiring multiple machines rather than getting one single machine that is super powerful, but also super costly. So next we're going to go back to this problem. Okay, what happens or rather that we look at some circumstances where we actually need to have a lot of data RAM just to demonstrate that this is actually a real problem that you would actually probably encounter, and it can actually crop up quite easily even from a simple example. Okay, so here's the example that we have. We are trying to see when we will actually encounter this billion rows of data. So I'm going to synthesize this data rather than trying to find a data set, because it's going to take a long time to just download that huge data set. So I'm going to synthesize it. So imagine we have a large data set with 10 million rows of data, and this will actually occupy quite a bit of RAM. So let's take a very well-known example of the IRIS dataset. The IRIS dataset has 4 numeric features: the sepal width, the sepal length, the petal width, and the petal length, as well as one output class variable. Now, each numeric feature, if we encode it using a double precision floating point, it will take up about 8 bytes of data to store each feature. And if we encode the class feature as an integer, this is also going to take up one single column with 8 bytes on a modern 64-bit CPU. So if we take a rough simplification, we can basically approximate this as 8 bytes times 5 columns, right? 4 columns for the input and 1 column for the output, which results in a total of 40 bytes per row. Now each row is not going to take much, right? First 40 bytes. But if we have 150 rows, this will take up 8,000, about 6,000 bytes. If we have 150 million rows, we just have to multiply by another million, and this is actually 6 gigabytes. Again, it doesn't sound huge, and probably this can fit within your laptop, but this is just for the data input, data training data itself. It really takes up 6 gigabytes of data. And if you have 1.5 billion rows, okay, well 1.5 times 1.5 thousand million rows, we would need this amount, which is actually 60 gigabytes of data, and this probably exceeds the RAM size of most laptops. So this problem can easily crop up even with a simple data set like this. It's just that whether or not we have lots and lots of rows of data or just a couple of millions of them. But you can see that it can easily crop up. Let's take a look at a code example to try to simulate that example that we had just now with the iris dataset in code. So I'm just going to, I'm not going to duplicate the iris dataset, but I'm going to simulate the amount of memory it takes. So the code here is going to use a large NumPy ND array as an experiment, and to simplify things, we are not going to encode the output as an integer, but we're going to just use the same size, right, but as a floating point number instead. So in other words, we would need 5 columns, each column storing a floating point number. We would import NumPy as NP and pandas, and then of course we also import other things like pyplot in case we want to plot it. Then we would just specify the number of rows that we want as 150 million. So 150 times 10. These two asterisks is actually to the power of, so it's 10 to the power of 6, which means it's 10 followed by 6 zeros behind it. So 150 million is the number of rows, and we are going to use the command np.random.random to actually generate the data set, because this command actually creates a floating point number, and you can specify the shape of the output in terms of the number of rows and the number of columns. So the rows, as I mentioned just now, is 150 million, and the number of columns, which is the second parameter here, is 5, because we have 4 input columns and 1 output column. So using this command and with the shape that we want for the output, we save the resultant NumPy dataset here in dataset variable, and if we print out the shape of the dataset as well as print out the size of the dataset in n bytes, or the number of bytes, you can see that the shape is what we expected, 150,000 followed by 5. This is the input, and the size is roughly what we computed just now, right? It takes up about 6 gigabytes of data just to store this 5 columns of data, because we have 150 million rows of data. Let's step up the game a little bit and we move on to the next example where we have even more rows of data. So the code is similar. So we're going to step up the number of rows from 150 million to 150 billion. And by billion, I mean 1,000 million. Okay, 1 billion is equals to 1,000 million. So this basically is 150 times 10 to the power of 9, or 9 zeros behind the 150. So it's a astoundingly huge number, but we do get data sets that are even a terabyte in size, or 1 trillion rows now, rather than just limited to a billion rows. Okay, so but let's try to see what happens if we use the same code as we have just now. We just import NumPy and pandas, etc., And now the number of rows we have changed. So previously it was 150 times 10 to the power of 6, but we have increased this to 10 to the power of 9. So it's 150 billion rows of data rather than 150 million. And same code again, we're going to use np.random.random to generate with the shape of rows and number of columns. So we only change the number of rows. That's the only thing we change. And then we can store the result back in dataset. And once it is finished, we try to print out the shape as before and also the number of bytes. And when we try to execute this code, it's going to generate a size that's much larger than before. Remember, previously we needed 6 gigabytes to store 150 million rows. And actually, the earlier computation we did is that we actually need 60 gigabytes to store 150 billion rows. Okay, I know your computer has a virtual memory and you probably have a lot of disk space, but what happens when we actually try to use pandas NumPy to just generate such a huge NumPy array? Would it actually print out the 60 gigabyte of data that we expected earlier? So depending on the machine that you try, if you try on your laptop, the most likely result is what we will see in the next page. Right? Your session has run out of memory because it has used all available RAM. In fact, I ran this experiment not on my laptop, but using a cloud service from Google called Google Colab, which has the default amount of RAM, limited amount of RAM of a couple of gigabytes, right? So 60 GB of RAM is definitely beyond what Google provides to you by default, and that's why it actually crashed with this message. Now, if you try a similar thing on your own personal laptop, it's most likely going to crash as well, because I don't think anyone would normally have 60 gigabytes of RAM on their laptop. But if we try with the National Supercomputer Center's AI server, it could be provisioned with more RAM, and you might not hit the limit with 150 billion rows. But what about 1.5 trillion rows? Yeah, no matter how much has been provisioned for you, eventually you will hit the limit if your data size is large enough. So this has to show that even for a simple data set with 5 columns, if you have sufficient number of rows of data, you will still run out of RAM eventually. So we need to think of ways that we can actually so-called distribute the load, or try to overcome this problem without always just stepping up to a larger and larger server. So we come to the end of this set of slides. So the main idea is to show you that even for a very simple data set like the IRIS data set, we can easily run into problems related to scale, such as the RAM constraint, and in the subsequent set of slides we talk about the CPU constraint and other problems that we may encounter and how do we overcome it. So thank you for your attention, and see you in the next set of slides.